Okay, so what we're going to do is we're going to go ahead and we're going to run that check for symmetry on that y equals x squared minus 2 graph. And so in order to do so, what I'm going to do is this. I'm going to kind of draw on a rough, crude sketch here. We said it had a y-intercept here, and it hit. You know, we explored this in previous videos. That x-intercepts positive square root of 2 and negative square root of 2 right there and there. So we've got our intercepts here, all three. But this was our graph, and we know that this exhibits y-axis symmetry. So in order to check for y-axis symmetry algebraically, what we can do is, now before we had even graphed this, we could have looked at this equation and verified we knew this was going to be symmetrical about the y-axis, which would be a huge, huge aid in helping us graph this polynomial in this case, but helping us graph this function in general. So to check for y-axis symmetry, what we'll do is wherever we see an x, and in this case you'll notice we have just one x in the entire equation, but wherever you see an x right here, we're going to plug in a negative x, okay? Which means this entire equation is going to maintain itself. Wherever we see an x though, we'll just go ahead and take that x out. So you know, we had one spot where we had x. Let's go ahead and plug in negative x. And I want to show you what happens here, okay? We know this is going to have y-axis symmetry, so this should result, according to our rules, the rules we had written over here, y-axis symmetry, it should result in the same exact equation we started with. So again, let's go ahead and verify this by looking at this. Now, this is in general, this equation, but if you kind of think about this, we're taking this negative x squared, and of course, you know, we're squaring the negative and the x, but anything times itself should result in a positive. So it would be fair for us to say that this would result in y equals, now this would just be a positive x squared minus 2. And you'll notice that this equation ended up the same exact equation as what we started with. Essentially what we're saying is this. No matter if you plug in a negative x value or a positive x value, you should result in the same y value, okay? And that's like us saying if we plugged in negative 2 here, we should get a positive 2 for y, but a positive 2 here, you get a positive 2 for y regardless. Okay, so how about we take an example in which maybe we're exploring something that you're probably not used to. You know, we're used to graphing functions. Let's graph something that's not technically by definition a function. So we say, how about this? X minus y squared equals 1. Okay, so a few things that I'd mentioned in the past. One very, very kind of useful thing to do necessarily would be maybe to isolate the y value. In this instance, I'm going to go ahead and start by making a table. But I think in this instance, it's going to be easier to isolate x. And the only reason I say that is because this x value right here doesn't happen to be squared. Okay, so nothing wrong with this. What we'll do is we'll add y squared to both sides. Gone. Okay, so we say x is equal to y squared plus 1. Now, this right here, you might say, would necessarily be a parabola if this y were an x and this x were a y. But what I want you to know is this, it's kind of like a parabola, but it's sideways. So it's really actually kind of nice to use this idea of symmetry here to graph something that's not necessarily a function. So here's what we'll do. We'll go and get started by making a table. And in this instance, let's go ahead and let's choose a bunch of y values to plug in and say, okay, so what would x be if x is this y squared plus 1? Okay, so how about we choose some y values here, and we'll go with convenient. How about 0, 1, and 2? If we were to plug in a y value of 0, you would necessarily see that, you know, this y value of 0 would be 0 squared, and 0 squared is 0, plus 1, we'd get an x value of 1. So we've got this point here, 0, 1. How about this y value of 1? 1 squared would be 1, 1 plus 1 is 2, so we'd have an x value of 2. Last but not least, 2. If we plugged in 2 for y, we'd have 2 squared is 4, 4 plus 1 is 5. Okay, so we've got a series of points here, and I'm going to go ahead and sketch these in. But there's an intent behind what I'm doing here. I'm trying to show something. So we say, okay, so 0, 1, that would necessarily be right there. Okay, 0, 1. We have 1, 2. Whoops, we'll go white. And then we have 2, oh, sorry. I've got all these backwards. This happens sometimes. I don't pay much attention. Okay, let's try again. We've got these series of x and y points, and maybe we flip our table around here. Maybe that'd be a little bit easier to see. I'm going to take the y and the x value and flip it back around. Apologize. But we say x's and y's. We have this series of points here. We say 1, 0, 2, 1, and 5, 2. This will look much better. Okay, so we had the first point here, which was 1, 0. 1, 0. The next point, which was 2, 1. This is much better already. And then the last point, which was 5, 2. Okay, 5, 2. But you can already see that we've got something that's kind of rocking like this. Here's the thing about it, though. In order to help us graph this, yes, we could check for intercepts right now. And of course, we have one intercept right there. That's our x-intercept. But this video is about symmetry. So we're going to check for symmetry, and we'll check for all three types, starting with y-axis symmetry. Now, I'm going to go ahead and spill the beans. This is not going to exhibit y-axis symmetry. There's going to be no graph over on this side, okay? But I want to check for this. So the way we check for y-axis symmetry is to take the original equation, okay, this original equation, y-axis symmetry. We'll plug in a negative x wherever we saw an x. Okay, so we say y equals, sorry. Now we're dealing with this equation over here. Wow, I'm way off the case here. We say x minus y squared equals 1. Let's start by checking for this y-axis symmetry again, which we said would not exist. But to check for y-axis symmetry, we plug in a negative for wherever we saw an x. So in this case, we say, okay, so here's my x. We'll take it out. And we'll leave everything else the same. And if I plugged in negative x, you'll see here already that this is about as far as it simplifies. And this is not identical to what we started with, okay? So in this instance, it would not exhibit y-axis symmetry. Now, I will say this. It is going to exhibit x-axis symmetry, but we want to show this. So to exhibit x-axis symmetry, we'll plug in a negative wherever we see a y. So we say x minus, and here we had a y. We squared, and we say 1. So if I plug in a negative y, here's what I want you to see. Often you get symmetry with things with even degree, and that is something that has an even exponent. And that is because when you take a negative to an even exponent, it tends to flip back to its original positive. But you'll see here that this is true. If we squared this negative y, you'd actually end up with x minus a positive y is equal to 1. And that's positive y squared. And this is exactly the same thing we started with. So we are positive. We are positive that this is going to exhibit x-axis symmetry. And that is important because, well, I can already tell you that this point here must exist on the other side of the graph, okay? So without actually having to plug in points or deal with things algebraically, I can already tell you that these points must exist. And we could actually, even without even graphing these 2 points, okay, we could necessarily just like sketch in, whoops, go away window, sketch in this part of the graph, okay, which would give us the rest of the graph. Now, just to verify a few things, that this did not have origin symmetry, that is, it was not flipped about this line. We didn't have some graph that, looked like this and kind of flipped over onto here. But we could check for this by plugging in a negative for all x's and a negative for all y's, wherever we see those. So I'm going to kind of take this up here and do this. But we say I had an x here minus a y here squared equals 1. Just took out all the x's and y's, that's all. Now if I plug in a negative x and a negative y, instantly what I want you to notice is this. This squared is going to act upon this negative, since it's squaring it, and flip this back positive. So what you end up with is negative x minus positive y squared equals 1. Now this is almost identical to the original. However, you'll notice here that this x actually it flipped into a negative, which is not identical. And therefore we can kind of show that this has no origin symmetry. So again, symmetry is great to check for because it helps you kind of get an idea of how you might sketch the graph in order to save yourself some time and just give you some more insight into how the graph looks.